All right, this is a video about conversion between rational exponent form and radical form. And we're going to start off with just a review of how this works. First of all, we know that by our equation here and by the definition of what a rational exponent actually is, that the denominator of that fractional exponent is the root of the radical that it is related to. And the exponent on top part, the numerator of that exponent, is going to stay with the base. So if we have 25 to the 1/2 power, then that's really the square root of 25 to the first power, which we know as 5. So that's what we're looking at here, except we're looking at it in a variable sense. We also know that it doesn't matter if you do the power inside first or if you take the root first. That's this version where they've pulled the power outside. That's because if you think of this as x to the m all raised to the 1 over n power, this is just multiplication, and multiplication should be exchangeable. So we should be able to do 1 over n and then m on the outside, which is this case right here. So that's what these are really saying, but that's in the exponent form. So we're going to use those to help us simplify and rewrite some things that are below. So this first one says, let's rewrite the expressions below in radical form. They don't want us to simplify anything, it just says to rewrite. So this one would be the 7th root of y, and then the numerator is 4, so to the 4th. This one, we don't usually like transforming it when the exponent is negative, just like we don't do many things when exponents are negative. So I'm actually going to convert that first to 1 over p, and then remember the exponent would now be positive using our exponent laws. So then this would be 1 over the square root of p to the first, which you can write the first if you want. Remember, the 2 is understood when you have a square root. Typically, we would rationalize this from this point, but it did not ask us to simplify. It just said to rewrite. C and D are an exercise in whether or not you're paying attention to your parentheses. So when we have a parentheses, so for example, a lot of students struggle with things like this. So this is just a little side note. When we have something like 2xy to the third all squared, how is that different than 2xy to the third? And maybe we want to say that just this part right here is squared. Okay, so we're just making sure you realize that the parentheses matters. So in this case, everything inside here is getting squared. So this would be 2 squared, which is 4. This is an x to the 1, so we use our power rule to multiply those. So that'd be x to the 2nd. And this is 3 times 2, so that's y to the 6th. Whereas here, notice the parentheses does not include the 2, so this would still be a 2, and the square is going to apply to just these two bases, so that's x squared y to the 6th. So in this first one, there's no parentheses, so this only applies to the x. So this would be 3 plus the cubed root of x squared. Whereas this is now all in a parentheses, so this is the cubed root of everything we had, so you don't want to drop the parentheses, 3 plus x, and then squared. So they're very different problems. Okay, for number 2, I wanted us to practice rewriting it the other way. So we're going to take these radicals and turn them back into fractional exponents. So remember, the denominator is your, it's going to be your root. So this would be x, and then this is 5 over 4. This one would be 1 over, so I'm going to do this first, and that would be y to the 3 over 2, because that's a square root. And they did say only use positive exponents, so we're going to leave it like this. If they had said, just use exponents, I guess you could move it up and make it y to the negative 3/2. But we wanted only positive exponents, so we're going to leave it as it is. In this case, we have that everything inside is being squared. Notice that. Everything inside is being squared. So this would be 4x to the 2 over 3. Whereas this is a little bit different. This is, if you think about it, this is 2 different pieces here. We could split this up into cubed root of 4 and cubed root of x squared. So this 4 actually has a 1 on it. It is not included in a parentheses. It's not being squared. So this would be 4 to the 1/3 times x to the 2/3. So notice this is different. All right, so let's talk about, and I just made up 2 different examples of why we want to know how to convert back and forth. So You could do this one with just exponent laws. You could just use your exponent laws, but then you do eventually have to do something with the radical because of the -8 in the bottom. But I'm looking at this and seeing an x to the 12, which is divisible by 3, a y to the 33, which is divisible by 3, and this is a cubed root, and -8 is also a perfect cube. So this might be easier to evaluate if we just change everything into the cubed root. So this would be the cubed root of all of this stuff, so x 12th, and then -8, and then y to the 33rd. And I'm actually going to use the variation where we put the square on the outside. So if we can take the cubed root of all these pieces, then we'll just have to square it to finish it. So remember, when you're doing cubed root and you're talking about exponents, you want to know how many groups of 3 are in 12. So that goes exactly 4 times. And then -8 is a perfect cube. -8 times, -2 times -2 times -2 is -8. So the cubed root of -8 is -2. 3 goes into 33. There's 11 groups of 3 there, so that'd be y to the 11th. The only thing is we have to remember to square what we just pulled out because that 2 hasn't been taken care of yet. So remember, this would be multiplication, so that would be x to the 8th. You do not multiply here. That's not why this is going to be a 4. It's because this is -2 squared. -2 times -2 is actually +4. And then this is 11 times 2 because they're both exponents. So that'd be y to the 22nd. So remember, exponents that are stacked on the same base, you do multiply them, but a number raised to a power, you have to do the actual exponent. Okay, and then the last example I came up with and why it might be useful to convert is because of this form. Sometimes you'll have two radicals that they're trying to get you to multiply together, but they're different roots. This is a square root. This is a cubed root. You can't multiply a cubed root times a square root in radical form. They're not the same thing. So what we can do is we can try to convert this to fractional exponents. This first one would be x to the 2 over 3 times, and this would be a 1 over 2, so x to the 1/2. Now we had a rule in exponents that said x to the 3rd times x to the 4th is x to the 3 plus 4. If you're multiplying, remember, same base, you add the exponents. So remember, this is one of our laws. We are multiplying same base here, so if we can add these exponents, we might be able to simplify this down to a single thing. Now, the problem is when we try to add 2/3 and 1/2, they're not the same denominator. So I'm going to do a little scratch work. 2/3 plus 1/2. I need a common denominator. So if I multiply this fraction by 2 over 2 and this one by 3 over 3, we get 4 over 6 plus 3 over 6, which is 7 over 6. So we actually get that this works out to x, and it's 7/6 as the exponent. If they needed that in radical form, we would say it's the 6th root of x to the 7th, which if they did want us to simplify, which we do here, 6 goes into 7 exactly one time, but with 1 left over. So we would still have an x inside. So this would be the radical form of the answer. This would be the simplified, this would be the exponent form of the answer. Let me correct myself. This would be the simplified radical form of the answer. So this is why we need to know about this conversion. It's because sometimes you'll get something you can't work out in one format, but if you convert it, you can work it out. I hope you enjoyed this video and that it was useful in explaining the difference between the two forms, how to translate them, and why they're useful.